Welcome, students, to another screencast with Mr. Swan. Today, we're going to talk about specific and latent heat, and I have a little simulation for you to look around and play with, and I thought about maybe changing things up a little bit. Nothing graded and nothing due. So today is more, hopefully, a day of learning and just kind of understanding, and latent heat and specific heat are something that you guys will use when you go off to chemistry, so hopefully this will find some value not only this year, but next year as well. And so we'll continue on. So picture of the day today, USS Stickleback's sunken location was found. This is the group I was talking to you about a long time ago, and their goal is to go find lost ships and submarine wrecks and possibly even planes that have crashed or have sunken down into the oceans. And they're pretty good at it. They've definitely found at least a few. This is the number 6 submarine that they have found. And where they found it is exactly pretty much where they believed it was sunk. This nobody has ever really gone down there to go take a look. But what happened is that this submarine and some more ships were working on a little bit of a battle and war maneuvers, and the submarine had was practicing, and they pretty much had some issues. Not really 100% sure exactly why, but they suddenly lost power, and they started to sink down, which then becomes a really big issue, because if you sink down into the ocean, you have more and more pressure being applied to the those vessels. And so that pressure could then, really destroy it, which would become a big issue for the crew inside. So the crew took a whole bunch of compressed air, and they used that to help the vessel rise again when they put them in the ballast tanks. And then once it rose, it was just a few hundred yards in front of an oncoming ship. This was all by accident. They saw it, the ship saw it, the ship tried to turn, but it was not able to do so. So the ship, which name is Silverstein, ended up crashing into the side of the submarine, which then caused damage and a little bit of a hole, which was not really enough to be repaired. And so everybody had to evacuate. And luckily for this one, nobody actually died. So the entire crew of the Stickleback submarine actually went on to the Silverstein ship, the one that crashed into it. And then they had some other ships in the area. They tried to pin the submarine and put cables underneath to try to hold it up, and it just didn't work. And eventually it filled up too much with water, there was too much weight, and they just had to let it go down into the ocean. And as it fell down into the ocean, it actually broke into 2 half pieces. So the bottom right photo is the picture of the submersible that went down there and was scanning it, and they found one half of the ship. They eventually found the other half, which is about 1,000 feet or so away. The top picture is where you can see the crew members actually getting out of the submarine, and they're starting to work their way on over into the ship to evacuate. So things happen, and every once in a while, I guess we lose a boat. But at least we found it, and so that's just one more that we have found. That ship is now under the authority of the Navy, and they will probably leave it alone. So they're probably not going to lift it up anymore. It's been too many years. It's pushing 60 or so. So it would probably be too fragile to kind of try to bring up, and not really worth trying to go down there. And nobody died, so there's no graves down there or anything like that. So they'll probably just leave it there. But it's nice to know that we actually found it, and we actually have another one. And there was another article that I was going to show you. I thought about making it picture of the day, but I just couldn't really figure out how to do it. It's called "Time Has No Meaning at the North Pole." And really, it was just an interesting article. It went on and talked about the scientists kind of working on these ships that eventually go all the way to the North Pole, and how it was different from the South Pole, because South Pole still has time zones, and that kind of follow whoever built those structures down the southern half of the world. But the northern half of the world is just water. So once you kind of get all the way up to the very top, you're in essence in every time zone all at once. So you just pick whatever kind of time you really want it to be. And then if this is during the winter, there's no sunlight in the North Pole. So it's just total darkness, and technically there's no time, so you just kind of make it. So it goes into what they actually did, how the captain actually went through and talked about the different time zones that he tried to manipulate it. So you had a Russian ship who was kind of coming into the area, and he wanted to have his time zone match up with them, so he just kind of maneuvered and changed it a little bit every day, and how people just adjusted to it. It's a very quick read. It was a pretty good article. No real pictures attached to it, so it's not really picture of the day, but I put the link up here in the slide. And just in case you wanted to go take a look at that one, I thought that was a pretty good article. Besides that, though, we will move on. So there's not really too many slides to do today. One is just on specific heat, and the other one is on latent heat. It is something that we have talked about, and takes some time to kind of understand. So I think we all know what heat is. Heat is just energy, and energy goes through these different atoms that makes them vibrate, and then their average vibration is what temperature is. And if they get more and they vibrate more, then it's more heat in theory than more temperature. And so that kind of goes. But things we don't always heat evenly, and that is something that we talked about on a lab a long time ago when we went to look at the temperature of how sand increases and how water increases. And we talked about how land increases very fast in temperature and water does not. And so the reason why, if you want to go to a very technical reason, is that water has a different specific heat than land does. And really, every object has a different specific heat than pretty much every other object. And it doesn't really follow any kind of general rules of, all solids have low specific heats and all liquids have high. They all kind of mix right around. So on the front page of your reference table, you will see this chart called the specific heats of common materials. And specific heat's definition is the amount of heat energy required to change the temperature of 1 gram of a substance by 1 degree Celsius. That's the top part of the slide. Hopefully that sounds kind of familiar. It sounds like calorie, because that's what calories do, right? They increase the temperature by 1 degree Celsius, and we need a certain amount of calories per day to survive, to keep our body warm. And the bottom left shows this chart, and that's what this chart is trying to go into explain, is that lead, copper, and iron on the bottom of the chart are fractions, right? So it's like a decimal of 0.45, 0.38, 0.13 versus liquid water, which has the whole numbers of 4.18. And really what this means is the higher the number, the more heat energy is required to go up a degree in temperature. The lower the specific heat number, such as lead is 0.13, means that it just needs a tiny fraction amount of energy before it goes up a degree in temperature. So this is why when you cook something on the stove, a metal pan will heat up very, very quickly, while the water inside does not, even though they're getting like a whole bunch of heat energy. The pan, like if you have an iron skillet, is a 0.45 specific heat, so it only needs a little bit of energy before it goes up a degree. But liquid water needs about 8 times more before it goes up a degree in temperature. That's why a metal pan gets hot so quickly. And on this specific heat right here towards the middle, it shows joules/gram times degrees in Celsius. What a joule is sometimes a little bit confusing. A joule is how we measure energy. And to give yourself an equivalent of like what 1 joule is, 1 joule is if you take something about the size of a deck of cards and you put it on the table. And so you have a deck of cards on the table in the packaging, right? And you go and you pick it up and you move it up straight up into the air about 1 meter tall. And that energy required for you to lift the deck of cards 1 meter up is about 1 joule of energy. So when we talk about 4 joules, it's not exactly a lot comparatively to us. Like we can lift a deck of cards 4 times for sure. But in that one motion of lifting that deck of cards up, which is 1 joule, water would only go up 1/4 of a degree in temperature, while something that is lead of the same size would go up like 10 degrees in temperature. So that's why this changes so much. Dry land is not exactly on this chart, so I put it on here on the right side. So dry soil, this is an average, has a specific heat about 0.8. So this is when we were talking in the weather unit of why land heats up very quickly and water does not heat up very quickly. The true answer really is specific heat is different. And the specific heat of dry land is 0.8, and specific heat of liquid water is 4.1. So water needs about 4 times as much energy to go up a degree than land does. And then to lose it is also the same. So dry soil only has to lose a fraction of 1 joule before it goes down a degree in temperature, while water has to lose 4 times as much before it goes down a degree. And so that's why when we talked about that law of thermodynamics, and the big part about that lab was if it increases quickly, then it must decrease quickly. And if it increases slowly, then it must decrease slowly because of specific heat, and you can't change that number. And the specific heat jumps around, so it also depends on phases. So it has liquid water, dry ice, and water vapor right here, the top three. You might notice that it's all water, but just different states can also affect the specific heat. So if you take a look at one of these charts, and when the lab, sometimes we maybe could have done it, but is if you wanted to heat up water, and you start with ice, semi-solid ice, and you increase the temperature, right? As the temperature goes up and as the time goes on, so it's the time of heat energy being applied, the temperature rises, and it goes up and it goes up and it goes up, and it goes the same. It goes up for solid, it goes up for liquid, it goes up for gas. The rate at which it goes up is determined by its specific heat. So this is kind of like a little bit new, and it's kind of a little bit old. So we already know that land heats up quickly and water does not heat up as fast. This is the true reason of why that happens. So over the course of a day, if you think about like how much land there is and how much water there is on the world, and how much sunlight's coming in, which is a crazy number of joules, and there's a crazy amount of water and crazy amount of land, that temperature swing over the course of the day kind of shows how much early energy is being applied to our Earth. It also talks about why land will change in temperature so much quicker than water actually will, which then affects the air pressure above it, which then affects how the wind moves, which then goes into sea breeze and land breeze. The next slide and the last one we're doing today is latent heat. Latent heat is very similar to specific heat, but it's a little bit of a different. It's all about phase change. So if you're talking about an object heating up, and it just, it's increasing from, let's say, 40 degrees to 50, and eventually 50 to 60, and you're watching it go up in temperature, that's all specific heat. If an object is changing states of matter, it's changing its phase, that is latent heat. So when you have a block of ice and it changes from solid eventually to liquid water, the heat energy required to allow those atoms to kind of break their hydrogen bonds to allow them to move more freely is what latent heat actually is. So latent heat, going right from the slide, instead of increasing in temperature, a substance can use heat energy to change its phase of matter, depending on how much heat energy it already has in it. So if you have, and chart is also on your reference table, right below the specific heat chart, it talks about how much heat energy is gained during melting. So for every 1 gram of ice, you need another 334 joules to change that solid ice into liquid water. If you went from liquid water and you wanted to change that into a gas form, you need to apply 2,260 joules for every 1 gram of that liquid water to be able to change into 1 gram of water vapor, in essence. So from going from solid to liquid, and it's 334. If you're going from liquid to gas, it's 2,260. So it's not the same amount per phase jump. It is quite drastically different, which is going to be quite important. So if we went back to my little chart that I showed you, this one, the reason why this chart is not a straight line and showing just specific heat is because we're actually showing different phases of water. We have solid on the bottom, then we have liquid, and then we have gas. So if you take ice and you heat it up, you actually will increase the temperature of ice. If you can have ice of a variety of temperatures, actually. So ice can be colder, if we're talking about just degrees in Celsius, it can be colder than 0. So let's say you have ice that's like negative 100, which is totally possible, and you increase the temperature of that, it's still going to be ice, and it will still be a solid, all the way from negative 100 to negative 90 to negative 80, and it goes all the way up until it hits 0. And then at 0, is when it starts to do its phase change. So if you're heating it up and you have a thermometer and like a beaker full of ice, you'll actually see the temperature stop, and it will stop rising. It will just stay constant because the temperature and the heat energy going into it is not being for specific heat to increase it in temperature, but is for latent heat to actually change its phase. So if you have time and you actually were able to do one of these, so if you got like a thing of ice and actually put a thermometer in it, and recorded the temperature like every 30 seconds or so for 20 minutes as you heat it up on a stove, this is the graph that would kind of start to form out. That the temperature can't go up until all the solid ice is gone because it's soaking up all that heat energy to change its phase into liquid water. As soon as the ice is gone, now you're right here on this graph, and then the temperature starts to go up again, going from like 0 to 10 to 20 degrees Celsius, like eventually to 50, and it works its way all the way up to 100. And as soon as you get to 100, all that heat energy being applied to that liquid water is not actually going up a degree in Celsius anymore. It is being used to change that liquid water into water vapor. And so that's where our latent heat goes. And so if you had this, this chamber of water in there, that heat energy would allow that water to change into a gas, and it would take time for that to happen. And because, it has to absorb 2,260 joules for it, with that number written on your reference table. And that time kind of goes on. And eventually it becomes all gas, and then the temperature can start to rise again. And then it continues to go up and up and up. So we call this latent heat, depending on like what you're talking about. If you're going from like liquid to gas, you can go this further and say latent heat of vaporization. If you're going from like solid to liquid, you can say latent heat of fusion. It just depends. A lot of times we just use the word latent heat to describe it in both ways. So you might be saying, like, how does this really affect climate? And now we're going on to our last little bit, and I'll include this link for you as well. It's a good kind of explanation of kind of like what is latent heat versus what is specific heat. It's a very quick read, just a few paragraphs really, and it goes down here to thunderstorms. So now this is where I'm going to say I had to gloss over this one for our weather unit, but we talked about like how do clouds form. I kind of got you by the time we left school to say, like the air is hot, it has water vapor in it, it's low pressure. Low pressure rises into the air, it eventually starts to expand, it eventually starts to cool, eventually hits the dew point, right? And then you're starting to get more condensation than evaporation, and then you have your cloud, and then it rains. What I glossed over is there is a step really between the cloud and the rain, of how big your cloud really can become, is all due to latent heat. Because if you went back to this slide where we were talking about latent heat, when heat energy is vaporizing, right? So if you're having water that's vaporizing, you're going from liquid to a gas, it's soaking in the heat energy into it to eventually allow the particles to vibrate enough to ping off. If you have the opposite, where you have a gas and it's going down a phase, right, into liquid, that's condensation. And so condensation is actually going to allow heat to go out into the atmosphere. And we talked about evaporation is a cooling process and condensation is a warming process. So kind of going back to my cloud here in this little picture, if that air is hitting the dew point, which is right here at the bottom of the cloud, and is condensating, that must mean that it's giving heat energy around to its surroundings, which is going to be really important because that heat energy that's going off is latent heat, and it has a fairly large amount of it, right? 2,260 joules per gram. And remember, clouds are many, many, many cajillions of grams. So that's giving off a ton of latent heat energy, which is causing all the air around those droplets to warm. And then warm air rises. And then it rises until it cools, and then it eventually cools until it gets to the point where that section of air must condensate, and then the process then gives off some more heat energy, and then air around that one starts to rise and then cools, and then starts to condensate. So that's how we get clouds at different heights. So when water vapor condenses to form a cloud, it releases that heat energy into the atmosphere. It's warming the air around those cloud droplets, right, causing those clouds to get bigger and rises further and further into the atmosphere. If that didn't happen, and we're kind of doing just what I kind of said before in the weather unit, you would get low-level clouds, and they would be relatively small because all the water would condensate immediately and then precipitate. But we know thunderstorm clouds from that cloud lab can be ginormously tall. That's how they get ginormously tall, and that's another reason why they don't happen during really the winter time. It's too cold. The air won't be warm enough to actually increase that size. But because water must lose heat energy to go from gas to liquid, and that heat energy goes around, it warms the surrounding air, it causes that air kind of around there to then eventually rise, which then condensates, which then allows even more warm air to kind of happen. And so then that's why we get these ginormously tall thunderstorms that rise through our atmosphere. So latent heat and specific heat, are useful in chemistry when you go and talk about reactions and changing the forms of matter, when you're going from liquid to gas and vice versa, for a whole bunch of different elements. Also useful for weather when we talk about, exactly like what happens to that heat energy. It just makes clouds bigger, which then in theory can make storms more violent, which then becomes a little bit of an issue. So another little thing for you guys to look at today is this one. This site is called FET. When they began a long time ago, they began with Flash, and Flash is going away. So they're slowly getting donations from a whole bunch of different places to try to remake all their stuff into HTML5. This is one that has been remade. The states a matter of basics. They really do have like hundreds of faces on here. Right now, I'm just going to stick with this one. So states a matter of basics states, and we kind of take a look at our ice. I'm going to change this to Celsius because you guys are more familiar with that one. And then let's do water molecules, and we'll just cool it down. If you take this little slider and you bring it down, so it makes a little bucket of ice, which makes it cooler. And like that's what solid water is. That's what ice is that you have all these water molecules bonded together, and they can move. There's still heat energy technically in them. They vibrate, but it's just a little bit. If you add more heat to them, and this is what my top thermometer is kind of showing, the temperature goes up. So right now I'm adding heat energy. It's being used, and in this case that we refer to as specific heat, right? Temperature is increasing. As soon as you get eventually to 0 degrees Celsius, right? That heat energy being applied now goes towards latent heat. So they're holding that latent heat, and then eventually goes into like liquid, where they start to kind of move around. You see like how they lost their shape? Like if you cool it back, let's cool it way back, right? They have like kind of a shape to them a little bit. These water molecules, they're kind of holding as best as they can. But as soon as we go to liquid, they lose that ability to do so they can start to move around randomly. If you increase temperature now, this is more specific heat. So temperature is going up. And then eventually once you get to 100 degrees Celsius, we'll pick up a pace a little bit. Right? Now they can eventually start to ping off and go on up into the atmosphere. So now that you have your gases actually starting to be formed. Should the temperature go up past 100? No. So what is the difference? Is that before we were talking about nature, and nature is like an open air container, that there's nothing preventing the air to expand and allow the water to ping off. We've learned that we can kind of manipulate this. And if we take stuff and we put it into a container and seal off that container, we can do a lot of things. We can actually get water to go to a higher temperature faster. And we're not talking about just a couple hundred degrees. We're talking like thousands to 10,000s of degrees, which allow us to make really cool things like new types of chemicals. It allows us to make new types of like medications for people. If you maybe have used a machine slightly similar to this, like called a pressure cooker or maybe an Instapot, at your house, right, is like it kind of holds the water in there. So now you're really combining temperature with pressure, which starts to really manipulate these things more. So when you guys go off to chemistry, that is something that you'll definitely be talking about, and how to manipulate the atoms a little bit more by adding pressure. So that is pretty much the end. We were just talking about specific heat and latent heat. The idea of today is just to get some understanding about it and see like why we use it. The more you learn about it, the better, because you'll use that when you go off to chemistry next year quite a bit. So that is all I have for you today. Just quick review: specific heat, heat energy used to increase temperature. Latent heat, heat energy used to change phases of matter. That is the big idea. I thought about having you guys actually do like a Google Sheet to actually and write out some things on this. I think I'm going to let that one go. I'm going to try to change this up maybe on a week basis. I feel like our Monday, Wednesday, and Friday lessons are going pretty good. I've talked to a whole bunch of teachers in the school. They have mentioned that students are maybe feeling a little overwhelmed on email. So I believe me only sending those 3 per week is pretty good. And to kind of lighten the load a little bit, because people are starting to feel maybe like a little overwhelmed. So if you're having any difficulties, please let me know. In the future, maybe next week, I'll try to do this. Like I'm going to call them live office hours. If you want to like sign in and then and chit chat a little bit, I'll be available for you to do so. So my goal is to set up the cameras and streaming for that this week. And that's about it for today. So hopefully everybody is doing well. If there's there's like a little bit of snow left outside, so hopefully you enjoyed that a little bit. But something to think about, and how to apply what you're learning to something else so you can do something not with a screen all the time, is think about latent heat and specific heat in terms of ice. If you happen to have a thermometer at a house and you actually want to go outside and grab some snow and kind of move it around and kind of stir it around and like eventually apply some heat to it, like you'll see that ice is melting and the temperature won't go up, which is a neat little phenomenon of what we're kind of working on today. So something a little non-screen for you to do. Besides that, I hope you have a great day and a good afternoon, and I'll see you around later.